So we've been working with vectors, and we're able to add vectors, we're able to subtract vectors, but the question becomes, how do we really multiply vectors, right? Because, if you have two vectors, let's say we have two vectors A and B, we know multiplication is repeated addition, but, how do we go about doing that with, vectors? Because it's like they each have their own components. Which components are you really repeatedly adding? So we need to come up with a way to multiply vectors that's really useful, right? Because vectors, these rules that we're constructing really have to define them. And we've defined vector multiplication in two ways: dot products and cross products. Today I'm going to talk about dot products. Here's how you take a dot product. So if I want to do A dot B, what I do is, what I'm really doing is I'm taking each of the components, right? A1, A2, A3, dot B1, B2, B3, and I have to, I don't know why I'm stammering over my words. What I'm trying to say is, you take the X components and you multiply them, so A1, B1, and then you take the you add the product of the Y components, A2, B2. Then you add the product of the Z components, A3, B3. And this sum of all the components multiplied, and then you add up each of the products, this is actually a dot product. And this is one way we can multiply vectors, where you get a scalar result out of this, right? A1, all of these A1, A2, A3, they're just numbers, right? Like, these are components. Like, this could be 2, 3, 4, 5, 1, 6. So, at the end, you're just adding numbers together, essentially. You're multiplying and adding numbers. This is a scalar quantity. This is a dot product, right? It's really not a crazy computation, right? If your vectors, like if you have v1, v2, dot u1, u2, to no surprise, this would just be the same as just doing a dot product, but now with one less dimension, right? You're not dealing with z components. So this is a dot product, and just like how there are properties for adding and just like how there's properties for kind of like adding and subtracting, there's also properties for dot products. If we follow that definition of what a dot product is, we find some pretty useful properties. We find that, hey, if you take a vector dot itself, you actually just get the magnitude of the vector squared, right? If you do A dot B, you actually get B dot A. And then I'm just looking at my note sheet here, if you're gonna take the vector A and you're gonna dot it with, I like to say dot, I don't know if that's mathematically correct, I'm just gonna say it, I'm sorry, it's just easy. If I take A and I dot it with B plus C, the vector sum of two other vectors, I essentially get A dot B plus A dot C. And if I do A dot 0, right, 0 being a vector with 0 magnitude, A dot 0 will just end up getting 0. And then C dot A, so if I scalar multiply one of the vectors in the dot product, so CA dot B is the same thing as A dot CB, which is also the same thing as this is the same thing as C times A dot B. So these are not like crazy theorems or properties. Like, this is just commutative one of these. This is distributive property, I think that's what it's called. This is, I don't know. It's one of the commutative or additive, or it's one of the properties where you can like change the parentheses. And this is these are properties we've seen before. We can prove them, right? Like, these are provable. Like, for example, something like this, right? Really, A dot B is the same thing, or A dot B plus C. This is the same thing as just doing A1, B, or A1, A2, A3, A3, dot, and what I'm doing is now I do the vector sum, right? So I'm doing the vector sum, which is just going to be B1 plus C1, B2 plus C2, B3 plus C3. So when I do that, when I take the dot product, I get A1, B1 plus C1, plus A2, B2 plus C2, right? I'm doing my regular, just what I define as a dot product. That's what I'm doing here. A3, B3 plus C3, where I'm taking the components, multiplying, and adding the products. So now, if I distribute the A component, so A1, B1 plus A1, C1, oh boy, plus A2, B2 plus A2, C2 plus A3, B3 plus A3, C3, Jesus. And then now, I can actually distribute. So I can say, or not distribute, I can like group them together, because I get A1, B1, and then, should I do it with different markers maybe? Yeah, let's do different markers. So I'm doing like, I have A1. So I have this A1 plus B1 term, I have this A2 plus B2, and I have this A3 plus B3. So I get A1, B1 plus A2, B2 plus A3, B3. And then now I have this A1, C1, A2, C2, A3, C3. So I have plus A1, C1 plus A2, C2 plus A3, C3. And then you can see, as clear as day, I essentially then get A1, B1 plus A2, B2 plus A3, B3. That's a dot product. I'm doing this is the same thing as doing A dot B, right? I'm multiplying the components and then adding them together, adding this products. And then same thing, A1, C1, A2, C3, A3, C3, that's the same thing as A dot C. So all these properties we're not just like transferring them. We're not just saying, oh, well, the distribution works with scalars, so it must also work for vectors. No, vectors are different from scalars. The properties may not always apply, but what we're doing is we're using the basic definition, and then we're working with scalars, right? With scalars, we know what we can do with, and then we're getting a vector result. This is really vector algebra, right? So just be mindful of that, right? Like, these aren't properties we're just taken over from the scalar world. These are like these can be derived from our definition, and they can be proved. So I know it was a little long, but now the next thing with dot products is, shoot, I think this theorem might have a name. It might not, maybe not, but it's basically the idea that if you were to take A1 dot B1, A dot B, remember, you can only do dot products with vectors. It's a vector operation, and the result is a scalar. And believe it or not, you actually get, when you take the dot product, it ends up being the same thing as just doing the magnitude of A times the magnitude of B times cosine theta, where theta is the angle in between. So A, B, and theta is the angle in between. So this is a really cool, useful like property, or I guess a theorem. You can prove this. I'm not going to prove this just to save time. I've made a video proving it, and I might make a new video afterwards. You can use a little hint if you think about law of cosines and think about how, you know, this would end up being B minus A. You can kind of go from there, or A minus B. Whoops. This is going to be the same thing with A minus B. But, yeah, A minus B. But what this kind of theorem tells us is, kind of gives us an idea about how parallel two vectors may actually be. So what do I mean by that? Well, when you take a dot product, you will sometimes get a negative value, sometimes get a positive value, and sometimes get 0, right? So if you think about a vector like, so if I do, I'm just going to do a random one. So if I do 3, 4, 1, dot, -2, 1, 6, I don't know what this will end up equaling, but I get, when I take the dot product, I get -6, I'm doing 3 times -2, plus 4 times 1, which is 4, plus 1 times 1, which is 6, I get 4, right? So this will end up equaling 4. That's a positive number. So a positive number, if my dot product ends up being positive, that means, well, all of these terms have to be positive. And obviously the magnitudes will be, right? The magnitudes A and B, the magnitudes of those will be positive. So my cosine theta has to be positive. So I know that if the dot product is positive, that theta, cosine theta first of all, needs to be positive. And for cosine theta to be positive, if you think about a unit circle, theta has to be in between pi over 2, or I guess not including, between pi over 2 and 0, right? And let's say theta is 0, right? Let's say they are completely parallel. Well, what that means is the dot product will equal the product of the magnitudes, which is that it'll end up equaling the product of the magnitudes. Now, if theta is equal, if I take this dot product, let's change this out to, I don't know, we can change just one of these to 0, right? If I were to take my dot product in this case, I have 3, negative 2, 4 times 0 plus 1 times 6. This would just end up turning 0 when I do 4 times 0. I get a dot product of 0. So if my dot product 0, one of these terms has to be 0, and it certainly can't be the magnitudes. It has to be cosine theta. So when is cosine theta equal to 0? It's going to be equal to 0 when theta is equal to pi over 2. So for, in this case, when theta is equal to pi over 2, that's when they're perpendicular. So they are not, so A, B are not are orthogonal. They're perpendicular with each other. And then if, let's say the dot product ends up being negative, so if A dot B, I guess, I don't know how I'm organizing this, but if A dot B is less than 0, then I know that cosine theta needs to be negative because the two magnitudes can't. So theta would have to be greater than pi over 2 and less than pi. And what that would mean is that the vectors are kind of the opposite direction. Now, obviously, they're not actually opposite directions. In that case, theta would be equal to pi, and that's when they're completely opposite. But you can see that there's it kind of looks like they're kind of diverging the other way, at least visually. But mathematically, I guess you can't really say that. But yeah, this is geometrically what a dot product looks like. So, if you want to, just as an example, let's say, hey, you want to find the dot product between, or let's say you want to find the angle between, and I'm looking from this from my notes, but if I want to find the angle between j hat plus k hat, and then b equaling I hat minus 2j hat plus, plus this 2 plus, and then minus 3k hat, right? How do we go about doing this? I dropped my eraser. So what I do is, if I'm doing a dot b, I would first do the x components. This x component 0 because I don't see an I hat term, and this x component is 1 because there's only the I hat component. So that would, when you multiply those, 0 times anything is 0. For the y component, for the y component's 2j hat, so that y component's 2 times 1 because it's just j hat plus 2. 2 times 1 is 2. And then same thing here. Minus 3 times 1, that's end up being negative 3 when I multiply the components, and I get a dot product of negative 1. And I know the dot product, based off that theorem, is equal to the magnitude of A times the magnitude of B cosine theta. So the magnitude of A is going to be square root, so I can drop the absolute values. It's going to end up being square root 0 squared for the x component plus 1 squared plus 1 squared. Then I have this magnitude of b, so 1 squared plus 1 squared, plus 2 squared plus negative 3 squared times cosine theta. So I can pull this off to the other side. Negative 1 is equal to, so we're going to have so this would end up being root 2, and then I would have root 4 plus 9 is 13 plus 4 is 14, and then equal cosine theta, and then my angle will be cosine inverse of -1 over root 28. So you can solve for this. I think it's like 100 degrees or something. I don't really remember, but makes sense, right? Because it's a negative dot product. So I know my negative dot product must be an angle greater than pi over 2 or 90 degrees. So last thing, a kind of an application-ish of dot products is the idea of projections. So I have a question. Let's say we have two vectors, A dot B, right? So if I have A like so, and I have B like so, let's say we want to find what is the projection of B onto A. In other words, what component of B is along the same direction as A? So, and not just the component, but specifically like, I guess let's start with that. The component, like, let's not worry about direction just yet. What component of B is onto A? Well, I know that if I were to draw it perpendicular like so, I have theta here, and I have this angle theta. So I know that the magnitude of B that's in the same direction of A, or the component of B that's on the same direction of A, right? Well, that would be the same as doing the magnitude of B times cosine theta. Because if this were a triangle, really I'm looking for this leg, right? This leg, that length represents the magnitude of B in the direction of A. So it's just B times cosine theta. Well, what's nice is I know that cosine theta, if I do magnitude of B, cosine theta, this is the same thing as the dot product. So let me write this out actually. So I know A dot B is going to equal the magnitudes multiplied times cosine theta. So if I rearrange for theta, I just divide by the magnitudes. I get A dot B over magnitude A times magnitude B. Oh, would you look at that? The those kind of they cross off, right? So the component of B projected onto A will end up equaling A dot B over A factorial, or not A factorial, the magnitude of A. So if I want to find, well, what's going to be the projection, what's kind of like the vector that has this magnitude in the direction of A, you can kind of think of it as like a shadow, right? Like this is like the shadow of B that's like projected onto A. Then what I would do is I would just take, so projection of A, or projection of B onto A is the same thing as the component of A, or B projected onto A, that is in the same direction as A. So to find the direction of a vector, I just take, or like the unit, right? Because I don't want to change really the I don't want to really change like the magnitude of this projection. It's still going to be that component. So I would have to multiply by a unit vector. And to find the unit vector that's in the same direction as A, I just take the vector A and I divide by its magnitude. So what I get is then I get A dot B over A, right? This is my derived formula for the component, multiplied by A over magnitude of A. So obviously once I simplify, I get the dot product A dot B over magnitude A squared times the vector A. So this is a vector result, right? I'm multiplying by a vector, and this would be a scalar result. So this has been dot products. Very useful for kind of things like work, right? When a force is doing work on a object, the angle between the displacement vector and the force vector matters, because work is really the dot product of those two. So when you're dealing with things where like only a certain component of the force is doing work, using the dot product helps us figure out, well, what component of the force that I'm exerting on a box is really doing work. So excuse me. Hopefully that's kind of all made sense. Ish, I guess. Yeah, this has just been dot product. I don't think it's like a crazy idea, but it sure as hell is very useful.